Okay, well, let's get started. Thanks a lot for coming today to join us for the Biard lecture in physics. Before we introduce our speaker, I'd like to say a little bit about the lecture itself. So this is the R. Jack and Forrest Lynn Biard Lecture in Physics. It was endowed by Captain Forrest Tex Biard and his sister Aubrey Trigg in memory of their parents. So there you can see the parents and Captain Forrest Biard here in this photo. So Captain Biard, so the last name is pronounced Biard. Captain Biard was born in 1912 in Bonham, Texas, and died in 2009 in Dallas, Texas. He served in the Navy, and for his service to his country, he was laid to rest in Arlington National Cemetery after he passed. He started his Navy career as an honor student at the U.S. Naval Academy, class of 1934. His first commission was on the USS New Orleans, shown here in this photo. And before the United States got involved in World War II, he was sent to Tokyo to learn Japanese language and culture. And shortly before the United States entered World War II, he actually escaped military detention in August 1941 and assisted in the escape of 10 other intelligence officers. During World War II, he had a variety of posts and stations, including Pearl Harbor, the USS Yorktown, shown there in that photo, Washington, D.C., Melbourne, Australia, and USS Wasatch. And he was a team of one of 12 Navy cryptanalysts and cryptolinguists in radio intelligence who was responsible for decoding Japanese naval and army codes. And he was, in fact, the last surviving pre-war trained cryptolinguist in naval intelligence. He played a role in the successful breaking of strategic code JN-25, which was critical to the Allied success at the Battle of Midway in 1942. And afterward, he was dispatched to Australia with General Douglas MacArthur to decrypt Japanese army code books that had been found in New Guinea. And he used these code books to decrypt communications about plans and troop movements for the battles for New Guinea and the Philippines during the island hopping campaign. After World War II, he returned to Japan as captain of the USS Luzon, which was a repair ship supporting the U.S. occupation forces in Japan. And then afterward, did his postgraduate studies at Annapolis and of the Ohio State University, where he studied nuclear engineering, nuclear physics, and radiation effects. Afterward, he was an operations officer for Ivy Mike, the first hydrogen bomb test in 1952. And then received his master's degree in physics from the Ohio State University, studying nuclear magnetic resonance. And then in 1955, retired from the Navy. The impacts of his Navy career, as you perhaps have gathered from the things I shared, were rather singular. They were summarized by some quotes from two fellow code breakers here. The fate of the nation quite literally depended on about a dozen men, this dozen cryptanalysts that I'd mentioned, that he was a group member of, who had devoted their lives and their careers in peace and war to radio intelligence. And had I not witnessed it, I never would have believed that any group of men was capable of such sustained mental effort under such constant pressure for such a length of time. Again, those are from two fellow code breakers during World War II. After the Navy, he was a professor of physics at Long Beach City College for about 30 years, where he developed a course on acoustics and the physics of music, which was later filmed and shown on public television. So he was a remote learning pioneer. His interests were in quantum physics, cosmology, and astrophysics, and he was a translator of Japanese history books. The Caltech connection is that he had a sabbatical here in the early 60s where he audited physics and astrophysics courses and had discussions with some of the great minds that were here at that time. And he had a fondness for his time here, and he wanted to endow Caltech with support to continue bringing people here to spend time and have great discussions, and so we're thankful that he and his family made that possible. And if you're interested in learning more about text or about some of these other code breakers, there are some links here. So let's thank the Biard family for supporting this lecture. While I transfer the setup to Eric Cornell, so that I can introduce him, and we can hear what he's going to tell us about. All right, thank you very much. So thanks again for coming. We're honored to have Eric Cornell joining us from Gilla today to give the first Biard lecture of this year. It's almost exactly 2 years since he was scheduled to give this talk, but traffic from LAX was slightly worse than usual, so he just got here. But either way, we're very glad that he could join us in person to give this lecture. Today he's going to tell you about a very exciting experiment to search for fundamental symmetry violations using trapped molecular ions. Though his research includes a very wide range of other topics in atomic, molecular, and optical physics. In addition to what he will discuss today, he's made important and foundational contributions to the study of ultra-cold quantum gases and their properties, notably including the first achievement in early studies of Bose-Einstein condensation in dilute atomic gases. Eric has too many awards to list. They include the Robbie Prize, the Benjamin Franklin Medal, and the Nobel Prize in Physics. Eric, we're glad you could join us today, and let's all join in welcoming Eric.
Thank you very much. I promised I would come. It's just taken me 2 years plus to fulfill that promise, and here I am. I have given remote colloquia, and it's been a long time since I've given a personal one, and I've never given a hybrid one, so I'm a little shaky on some of these things. But Nick, you'll be able to admit people because people keep popping in and want to be admitted, and I feel bad if they're hanging out.
Yeah, I'll keep an eye on it.
All right. So we're going to talk to you today about the doctrine of original imperfection, and in particular about the electron-electric dipole moment experiment going on at Gilla, which I've been doing now for more than a decade with Jun Yi and myself as co-PIs on the project. Okay, let's try. The clicker advancer was working great before, and now it's not. Let's try this.
Try clicking in the window.
Oh, that's a good idea. Let's try that. All sorts of exciting things are happening. Let's try this. There we go. There is the group that's working on the electron-electric dipole moment experiment. I'd like to introduce just a few of them. One is Jun Yi, one of the world's great laser spectroscopists. He and I have been working on this project together for quite a long time. Tanya Rusi and her colleague Dr. Luke Caldwell are the two senior people on a new measurement of the electron-electric dipole moment that I wish I could tell you about today, but the data are due to be unblinded within the next month or so, and that's coming along very well. Xiaobun Ying is the senior graduate student, senior laboratory person on a new generation of EDM projects coming out of my lab, which won't be ready for another 3 or 4 years or so. He's led that. And I just want to offer my congratulations to Antonio Vigil, who graduated summa cum laude with a wonderful honors thesis in our lab just a couple months ago. Okay, starting with Bang, 14 billion years ago, we had one. And 14 billion years later, here we are to talk about it. If we advance in time just a few milliseconds, we look around and we find a huge, I believe the creation hymn says the whole universe was in a hot, dense state. There were electrons, protons, anti-electrons, anti-protons, and so on, an enormous soup. A few more milliseconds after that, the universe has expanded and cooled. And over the course of about a second or two, some very romantic things happened. Electrons found anti-electrons. Neutrons found their soul partners, anti-neutrons, protons, anti-protons, and so on. It was wonderful, but the relationships were short. And one by one, they annihilated each other until they were all gone. And this was happening all around the universe. There was, right after the Big Bang, about 1 billion times more stuff in the universe than there is now. And all about a part in a billion of it found about 1 part in 1 billion of the particles in the universe found their soulmates and annihilated. There was somebody for everybody, almost. There were just a very small number of matter particles, electrons, protons, neutrons, and so on, still available. So the question is, who are these final few lonely particles that no one wanted? They are you. I feel like sometimes explains a lot, really. What was nearly perfect, this matching up of matter and antimatter to the part per billion level, was not exactly perfect. And this not exactly perfect is what we call the doctrine of original imperfection. That's why we're around, and it's good. We'd like to understand it. This original imperfection is sometimes known as matter-antimatter asymmetry. It was described in the book of Baryogenesis, a long-lost text which is no longer available, because when we had said all about it, but we no longer can read that book. And it was a T-violating and a CP-violating event. Basically, one of our basic, almost always obeyed laws of physics was violated in order to have this asymmetry, which was so very, very important. It was the asymmetry from which we all came. It happened a long time ago, so we can't go back and look at it, and it cannot be explained by the particle physics of the standard model. So how can we learn more about it, given those two limitations? I like to, okay, so it was a long time ago. There are no time machines, so we can't go back and look at it. There are no documents left over. And so I have this metaphor of a three-legged stool of various different ways of going back and looking at those things. And one leg of that stool is telescopes and telescope-like things. This is, I think, an artist's conception of an enormous European space telescope. When I say telescopes, I use the term very broadly. I definitely think of LIGO as being a telescope. Gravity waves are another kind of telescope. I think of neutrino detectors as another kind of telescope. All these things are useful for sort of looking out into the universe and seeing what's going on. And you can think of a telescope as a look-back machine. If you look at a galaxy which is 10 million light years away, you see that galaxy as it was 10 million years ago. The farthest away galaxy you can see is 13.3 billion light years away, and you're seeing this galaxy, when you look at this galaxy, you're seeing the universe as it was when the universe was only 4% as old as it is today, but that's not nearly far enough back to see these effects, to look into the universe at a time when matter and antimatter were undergoing, experienced this slight imbalance. So another way to get at these things is with particle colliders. You can smash two particles together, and you can think of that collision as a simulation of the very hot, dense, and violent early universe. The largest scientific instrument ever built, the Large Hadron Collider, spans many, many miles, many kilometers, has detectors which are, you can see a tiny person in there, which are, dwarf the human scale. And yet, apparently, from what we've seen so far, it's not able to address that question. The energies it reaches do not reveal to us particles which seem to be sources of CP violation that can account for this original imperfection. And building a bigger accelerator might take roughly 30, whether you're measuring it, it's supposed to say 30 years or $30 billion. It could take a long time and a lot of money, and might or might not happen. So those are two legs of a stool, sort of a tripod that allows you to sort of learn new things about things from long ago or at high energy. And for particles, you must wait a long time before they're able to build a new one. For telescopes, you don't have to wait a long time, but it happened only one time. And all I mean by that is that astrophysics is an observational science. You don't get to tinker with things. So you can learn amazing things, but you don't get to do experiments as we usually understand them. So the third leg would be precision measurement, and that's what I'm here to talk to you about today. Here we are using a very precise device to measure a fossil, which is supposed to help us think of seeing things that happened a long time ago. When we want to study dinosaurs, we look at dinosaur fossils. If we want to study ancient physics, we can look at physics fossils. When we're babies, one of the first things we learn as babies is we learn about the idea that, objects, permanence of objects, things that are around tend to stay around. It's something we all take for granted, But it's new to babies, and because it's so new and babies find it so very interesting, that's why babies like to play peekaboo. Things disappear, they reappear. How fun is that? You probably don't remember it, but babies think this is hilarious, and if you're a parent of a baby, as I once was, twice, it's also fun. But that's what they're learning. This is why it's such a tickling event for small children. And of course, as physicists, or astrophysicists, or people sufficiently interested in physics to come to a physics colloquium, we also once were physics babies. And we believe, rightly or wrongly, in the permanence of physics. We think that we like to believe, and you could call it an article of faith, but we want to believe that whatever physics was around in, say, the first 2 or 3 seconds of the universe that caused the CP violation, that caused us to exist at all, we really want to believe that physics is still around, still with us, and it just happens to be playing peekaboo with us, where basically it's having a little fun with us, appearing, disappearing, we don't see it. I can't really say that for sure, right? I don't actually know that the physics today is the same as the physics as it was 2 or 3 seconds after the Big Bang, but I really want to believe it. So I'm going to go ahead and base it on that. And so what I want to say is that physics that was around there, the fossils of that physics, just like the fossils of dinosaur bones are permanent, so should that physics be permanent. And we should look for places where we can see extremely small CP violating effects in particle physics now. Our particular approach is to look for CP violating physics in the electron's electric dipole moment, EDM. Here in Caltech, people are also looking for CP violating physics in baryons and neutrons, a very large project here. And there's also an electron electric dipole moment experiment going on here too. So we're not alone in this. It seems like a promising direction to look for things. Oh, there's Mr. Electron. What do we know about him? He's got a charge of -1. He's got a mass. He's spinning. So he's got a magnetic moment. He's got a north pole and a south pole. Used to be, from a physicist's point of view, that's about all you need to know about an electron. At least that's sort of the EV scale. But it's also possible that the electron has an electric dipole moment. That is, in addition to its big negative charge, it's got a little positive charge near the pole and a negative charge near the other pole, or vice versa. You can think of the positive pole, that little tiny positive charge adding destructively, and little negative charges adding constructively. For a charged particle, an electric dipole moment looks like the center of charge is not exactly in the same place as the center of mass. And that offset is a perfectly good way of defining the center of mass of a singly charged particle. We can measure it in centimeters. If it exists, it violates the fundamental symmetry T and fundamental symmetry P and CP. And let's ask ourselves, how might it be? How big might it be? By the way, not to give too much away, but so far no one's ever been able to show that it does exist. It just seems like there's a lot of reasons why it might. So we're saying we want to describe this electric dipole moment as a length scale. So what are the sort of natural length scales we have available to us if we are an electron? Well, one is around a hydrogen atom, which is, from an atomic physicist's point of view, and a hydrogen atom is just an electron. I realize that there's a proton in the middle of it, but it's not very important for atomic physics, so we won't get into that. Really, all the properties of a hydrogen atom are in its electron, and in particular, it's got a dipole moment, a fundamental electron transition moment, which is basically 1 Bohr, half an angstrom or something like that in size. That's one way you could talk about it, a sort of a useful length scale. Another length scale is smaller than that by the basically 1 fine structure constant. I grew up using units where magnetic moment and electric dipole moment are measured in the same units, and so that's basically this size of the hydrogen atom times the fine structure constant. That's actually the magnetic moment, not the electric moment, but the magnetic moment of an electron. Or you could take the classical radius of an electron, which is just you take the 1 unit of charge, 1 fundamental charge, and classically squeeze it down. And as you squeeze it down, there's more and more Coulomb energy. And when that Coulomb energy equals the relativistic rest energy of an electron, that's a radius. And that's smaller than the Compton radius by another factor of the fine structure constant, about 3 Fermi, it turns out. There's another length scale. Then there's like an empirical length scale, which is, suppose you wanted to see, does the electron have any structure? Well, one way of finding out structure is you could do a scattering experiment. To do a scattering experiment, you have to smash something off of it, and the most energetic things we have to smash off of them are at the LHC, and That in principle could look all the way down to about another 5 orders of magnitude or so, 6 orders of magnitude smaller. The current experimental limit, which is not done with a scattering experiment, but spectroscopically by Acme, which used to be a Harvard and Yale collaboration, now it's a Harvard and Northwestern and Chicago experiment, is 16 orders of magnitude smaller, 16 orders of magnitude from the classical radius, which is like sort of the smallest natural length scale I can kind of associate with an electron, 16 orders of magnitude smaller than that, consistent with 0, that's the current limit. And we'd like to do another factor of 10 or another factor of 100 better. What would be the significance of that? I am not a particle physicist, but I'm able to read some particle physics papers, and very roughly speaking, on general grounds, if I have sort of a one-loop diagram where I've got an electron, and it's interacting with an electric field, and it's generating an electric dipole moment, that could come from basically, this is an old slide. It used to be everyone's favorite extension to the standard model was supersymmetry. So this is why it's SNU physics, but it's probably not that anymore. You emit some sort of massive particle, and these three lines are all some sort of exotic new particle, and this could give rise to an electric dipole moment, and we can scale that electric dipole moment by the classical radius of the electron, and do a very, roughly speaking, model-free, but not exactly calculation. There's plenty of adjustable parameters, but it gives you the scale of this, and it's given by some mixing angle and by the ratio of this new particle mass to the electron mass squared. That's how we would compare it to the classical radius, which means to say if we come down to 16 or more orders of magnitude smaller, we would be sensitive to particles whose, if we make some sort of naturalness argument, particles which are, say, 60 eV, new particles, which should be compared with the most recently discovered particle, which is 60 times smaller. So it seems like a promising way to poke around and find new particles which could be giving us possible new physics. And if we could only go, say, even another factor of 10 or more smaller, we could go even higher, maybe up to 20 TeV or something. So that's the name of the game for us. How do you measure an electron-electric dipole moment? Pretty much the same way you would measure a magnetic dipole moment. You want to measure a magnetic dipole moment, you put an electron in a magnetic field and you shine a radio wave at it and it flips over. That's electron spin resonance. And the frequency at which it resonantly flips over, that's just the magnetic dipole moment times the magnetic field. If we add an electric field, and if there's an electric dipole moment, the frequency will shift a little bit. We could do this experiment twice, once with the electric field pointing along with the magnetic field, once pointing the opposite way. We'd see two separate resonance lines, and if we subtract the centers of those two resonance lines, the magnetic field, which maybe we don't know all that precisely, but the difference in those two resonance lines, that's the electron-electric dipole moment times the electric field. Conceptually, it's a dirt simple experiment. This is a sort of 1940s era experiment. It's just hard to do it really well these days because you want to measure something which has already been shown to be, if it exists at all, really small. So how do you do a really good electron-electric dipole moment? One is you want to have a really big electric field because if the electric dipole moment is small, you want a really big electric field to bring this out. You want to have really long coherence times so that your resonances are narrow and you can distinguish them one from another. And you'd like to have really high count rates so that you can find the center of these resonances super well. You have a figure of Biard. Big electric field, effective electric field on the electron, long coherence time, hopefully a big count rate, and then you can make a good measurement. The problem is if you apply a big electric field to an electron, what does the electron do? We learned about this as first-year students, at least. The electron goes flying away. And it was Pat Sandars from Oxford who said, well, if we attach the electron to a very large, heavy nucleus, first of all, it keeps the electron from zipping away, and it also gives us a relativistic enhancement proportional to the protons in the heavy nucleus. So that's nice. Our approach is we actually embed the electron that we want to measure in a nucleus, in a molecule, and inside a molecule, like I never took chemistry in high school, but my understanding is the way molecules work is some atoms are positive and some are negative. Now, chemists tell me that's not how it actually works, but suppose it were. And right in between, like sodium is positive and chlorine is negative. That's what I learned in high school from chemistry. That's about all I remember. Imagine that you're living right in between the sodium and chlorine in a molecule. There's going to be a big electric field there. Sodium and chlorine doesn't have it. Sodium chloride, salt, doesn't have any unpaired electrons, but other molecules do. We happen to work with something called hafnium fluoride, and for a relatively small electric field in the lab, about 10 volts per centimeter, the electrons, this small electric field causes the molecule to be polarized, and the electrons feel this much, much larger electric field inside the molecule. It's a way of it's like a way of amplifying the magnetic field by about 9 orders of magnitude. So it's a super powerful way of looking for electric dipole moments by getting a really much, much larger electric field than you could ever generate in the lab. If you try to make an electric field in the lab of 10 to the 10 volts per centimeter, you just get sparks. Then you want a long coherence time. We actually work with a molecular ion. Trapping molecules in ion traps are relatively easy. Just to quickly compare the two leading experiments, which these days are JILA and ACME. JILA is University of Colorado. ACME is this multi-university collaboration. We use a heavy metal fluoride. They use a heavy metal fluoride. We get big electric fields. We use ions, which ions suffer space charge, so we don't have that high a count rate. We can't have that many ions detected at the same time. ACME uses neutral molecules, gets a much larger count rate. We use a trap, so we have a coherence time which is 1,000 times longer than ACME, which uses a linear beam. Basically, Norman Ramsey or Robbie would have recognized this apparatus. The atoms just travel once through traveling 100 meters per second down the beam line. They have much, much broader resonances, but because they're neutral molecules, they can have a much, much higher count rate. And surprisingly, all these effects roughly cancel out, and we're at very, very similar accuracies, these two experiments. We and JILA have to work in a rotating frame of reference. I'll get to that in a second. ACME doesn't have to worry about that. Coming soon, like say here at Caltech, there are people who are talking about putting the good things of these together, having long coherence times because they use traps, but high count rates because they use neutral molecules. To do that, you have to trap neutral molecules, which is hard compared to trapping ionic molecules. But Caltech professors are not afraid of difficult experiments, so they are a terrifying thing for those of us who are in competition about this, but we'll soldier on. That's coming soon from Nick Hutzler, for instance. So you want to do trapping. The whole point of trapping particles is you have inhomogeneous electric and magnetic fields. The inhomogeneity of the electric and magnetic fields pushes the atoms, the molecules into the center. And on the face of it, you might think that inhomogeneity is like a very bad place to do precision metrology because you get line broadening and what have you. We take advantage of a really cool idea from Dave DeMille, who pointed out that certain molecular states come in pairs of, have very closely spaced states of opposite parity. And if you apply an electric field, those states polarize, get remixed into states of good projection directions, like the molecules pointing either up or down along the electric field. If you add to that a magnetic field, those states shift up and down. And then if the electron is living inside the molecule and it has a small electric dipole moment, those states are even a little bit further spaced. So if we measure that transition, and we subtract it from that transition, basically the effect of the laboratory electric fields and the laboratory magnetic fields subtract out. And all that's left is the internal electric field of the molecule, very uniform, very constant, given to us by God, if you like. And all the inhomogeneity cancels out. And so it's an extremely precise and stable measurement, which you can do in the relatively hostile environment of a trap. So this is a clever idea. It's sort of got a built-in, call it a built-in co-magnetometer. These two states have very similar magnetic moments. You can subtract them out. Well, we do have to apply an electric field to cause the ion to be polarized. How would you do that? Our ion, of course, we have an ion trap, and if you apply a large electric field to an ion, it polarizes the ion, but it also causes the ion to fly away. Did you see that? That is very high in, I think we better look at that again. That is high in PowerPoint right there, folks. Look at that. All right. How can we do that? How can we apply a large electric field? Well, we could use a heavy ion storage ring. If you have a heavy ion, like this one, this is a storage ring, I think, in Switzerland or France, and there's a very heavy ion inside there. And if the ion is going around in a circle, that must mean there's constantly an electric field on it. It's always just pointing inwards. Well, I am nothing if not visionary, so I go to the chancellor and I say, we could build this here in Boulder. We'd have to have a large counting station here. We'd have to demolish the football stadium, but I see that as a feature. The chancellor said no. So I said we could make it smaller. No. We could just put it on the grass outside of Gillett. No. God, what a grunt. So we moved our large heavy ion storage ring inside Gillett. I like to show this picture, especially here, because this dates back to a famous happy time when my lab was more than 50% former Caltech people. Matt Grau was an undergraduate here. So was Kevin Cassell. Conquan Nee did her postdoctoral work here. So that was a wonderful time, powered by Caltech about 10 years ago. But also I put them here because these people can show to scale the size of our heavy ion storage ring. We have to zoom in a little bit. Well, there it is. Our storage ring is 1 millimeter in diameter. It doesn't actually live on Matt's shoulder. And we don't actually have a storage ring per se. We just have a ion trap with a rotating electric bias field. So the electric bias field rotates around, and the ion rotates around at the same time. And our trick is basically to have the bias field rotating rapidly enough that the ion doesn't travel very far before the electric field changes direction. So the ion just goes around in a relatively small little circle, about 1 millimeter in diameter. But it's rotating, the rate of rotation is slow enough that the molecule has plenty of time to adiabatic. Any given time, the molecule is adiabatically pointing along the direction of the electric field, which means that we have a well-defined, laboratory-defined axis of quantization in which to do our measurement. It happens to be rotating, so we have to do our spectroscopy in the rotating frame, and therein lies 5 years of theory, but we know how to do it. Okay. This is what the apparatus looks like. For scale, you can see the standardized. I work for the National Institute of Standards and Technology, and all needle nose pliers are exactly 5 centimeters long. That's for scale there. The spacing between these electrodes is just under 10 centimeters. There's 8 of them. They look like fins, and the molecule is confined. We put electric fields on those fins, 45 degrees out of phase, oscillate around. And in the center of those fins, we have a very uniform rotating electric field. Additional electrodes provide confinement, and the whole thing goes inside an ultra-high vacuum chamber for our trap. The experiment looks kind of like this. We've got a solid metallic rod of hafnium. Hafnium fluoride plus, for various reasons, is our favorite molecule. It's not, it was one of those molecules out of a chemistry exam the professor would mark it wrong. Like, this isn't even really a molecule. It's not stable. It only exists in vacuum. So we can't let it touch anything after we make it. We ablate the hafnium with a laser. The hafnium vapor mixes with some sulfur hexafluoride, a gas. And then chemically we get hafnium fluoride neutral molecules. They travel into the center of those fins, and right when they get in the center of the fins, we ionize, we knock an ion off, and stop the ion in the middle of our trap. We apply the rotating electric field and many, many more lasers in order to prepare the initial quantum state and read out the quantum state. And as our final detection thing, depending on whether the direction of the electron spin, contingent on the direction of the electron spin, they can absorb some of these photons and fly apart and dissociate or not dissociate. So when we kick the ions out of the trap onto an ion detector, they arrive with a time lag in between them, and we can tell what state they were in. So we prepare and read out the quantum state. Just to give you a sense of scale, these ions are sort of oscillating slowly back and forth at a couple kilohertz. They're rotating at 375 kilohertz. The confining fields have their own characteristic frequency. But yeah, I think that generally because the quantization axis is rotating in time, it's relatively insensitive to any sort of laboratory DC field, so we don't actually have magnetic shielding around the outside. There's an extremely complicated sequence of laser pulses and electric fields and magnetic fields turning on and off to do the various spectroscopy. Happily, we have computers who never get tired or bored and can do that the same every single time. The laboratory looks like this. It's basically a laboratory full of lasers, and you can barely see in the back the experiment, which is a small vacuum can that has that ion trap I showed you. We measure basically the frequency between these internal states of a molecule and these internal states of a molecule, which corresponds to the electric field pointing along with the magnetic field or against the magnetic field. We measure these two frequencies simultaneously. Some of the population is here, and we measure that simultaneously with the population here oscillating back and forth between these states and the population here oscillating back and forth between these states. We read out two sinusoidal frequencies at the same time, and we look for small differences in those frequencies, which is the signal for the electric dipole moment. There's actually many different things we can change in the experiment. The magnetic field can point towards the center of the trap or away from it, so can the electric field. The sign of the rotation can be clockwise or counterclockwise. There are 8 possible linear combinations. So we measure these 8 different frequencies corresponding to these 8 basic different configurations of the experiment. There are 8 possible linearly independent combinations of those frequencies. Just one of those frequencies is sensitive to the electron-electric dipole moment. The other ones, and the electron-electric dipole moment, most of the systematic effects cancel out. The other frequencies are interesting to measure because they tell us all sorts of things about the condition of our trap, how uniform our fields are, and what have you. And by looking at these 8 different frequencies under various different conditions of the experiment, we can probe to see what sort of systematic errors we have. Because at the end of the day, that's what we spend 95% of our time doing, is trying to understand what kind of errors we have in our data. A possible source of data of error, which we worry about a lot, is called Berry's phase, which is a sort of glamorous thing. It used to be people talk about it a lot. Imagine you have a spin, and the spin is projected in a quantization axis, and the quantization axis slowly over time traces out some little circle. You can sort of imagine that this quantization axis is sort of sweeping out the side of an ice cream cone. That circle, if it's got a solid angle, call it A. Then after you slowly come back again, slow compared to the energy difference of spin up or spin down along the quantization axis, you pick up a Berry's phase, which is a difference between the molecules which are projected one way with one value of m along the instantaneous quantization axis, or the other way along the instantaneous quantization axis. You pick up a phase. And if you're sort of constantly tracing that out, you pick up that phase every time you make that little shape. And that phase, you pick up a certain amount of phase per time, and that can become a frequency, a systematic error. So that's something we worry about. And why do we worry about it? Because we are rotating. The molecules are sitting in an electric field, which is the quantization axis, and the electric field is rotating in time. This is the quantization axis. It points along the equator, and 375,000 times per second, it traces out a circle. That circle has got a solid angle, which is 1/2 of a sphere, so that's 2 pi. Delta m, the projection, works out to 3 h bar. So what you end up finding out is that the natural scale of this Berry's phase frequency shift is 750 kilohertz, and we're trying to do spectroscopy at the level of about 30 microhertz. So on the face of this sounds like a scary environment. What it helps is that if the electric field is exactly pointing in the equator, and you go all the way around, that's exactly 2 pi ster radians, 1/2 of a sphere. Delta m is exactly 3. That's a quantized number, so it's 6 pi ster radians. If you you're doing spectroscopy and you add 6 pi radians onto something, 6 pi radians Berry's phase shift, 6 pi is the same as 0, right? That's in spectroscopy, everything is modulo 2 pi. So you might say, well, what if there's a very small electric field pointing upward, and this is instead of the circle tracking exactly along the equator, it's tracking slightly above, like 1 degree north latitude, 2 degrees north latitude, or 2 degrees south latitude as it goes around this imaginary sphere. That would be a large frequency shift. What saves us is that if there were an electric field pointing up, this is a charged particle. A particle will move. It will move up in the trap until the trapping fields are just such as to stop it from moving. That's what traps for ions do. The very fact that your ion is trapped tells you that the average electric field where you're trapped has to be 0, or the ions would go somewhere else where it is 0. So the up and down electric field very, very precisely cancels out, which means that the corresponding solid angle is very small, And then as a final check, we do the experiment rotating in the clockwise direction, and then we do it again rotating in the counterclockwise direction, and we get almost the identical frequency in the two different directions. So everything cancels out. It works. That's in the end all I can tell you about that is that it works. Most of the time. The fact it has a rotating field gives us great immunity to stray fields. But we do find that as we change the sign of rotation, this is like one of those linear combinations of frequencies, and that corresponds to a rotation odd frequency shift. We do see some shifts in the frequencies, especially if we move the ions away from the center of the trap. Here's measuring various frequencies in the trap as we can use static electric fields to move the ions from one side of the trap to the other along the north-south axis. These red lines correspond to different locations vertically. And we measure all these different frequencies, and we spend a lot of time thinking about what they mean. These particular frequencies say, your fields in your trap are not as homogeneous as you would like to believe. Yeah, and the fact that those three lines don't all kiss each other, but seem to be missing each other, what that's saying is, when you apply voltages onto your fins, there is some current running down the fins, displacement currents, to apply those voltages. That's what that tells us. We're not especially surprised to see it, but that tells us exactly how much it is. So we take a lot of data that looks like this and understand what it means. This data was taken in an obsolete trap with much, much worse electrodes than we have now. So you wouldn't see anything like this now in a more modern trap. This is how we spend, as I say, about 95% of our time looking at stuff like this, understanding what it means, and trying to understand how much it's going to hurt us. How badly does nature hate us? We know that nature hates us because we're trying to make precision measurements. That is how you have to go through life as a precision metrologist. But you want to know how nature is expressing its particular hostility to you, and that's what these data tell us. And what can we do about it? One of the things we do about it is we take data blind. We like to think of ourselves as honest and ethical scientists. I really think we are. It doesn't matter how honest you are. It doesn't matter how ethical you are. There is an enormous psychological pressure to look at your data and see what you expect, or maybe even deeply want to see. It's all but overwhelming. Nobody is immune. The computer, on the other hand, doesn't care about the number at all. We've checked. We query it. Alexi, do you care what the Alexis? Do you care what the electric dipole? No, I do not care. Fine. We tell it to lie to us. It basically analyzes the data and adds a random number to it and tells us it doesn't tell us the random number. So when we are looking, but it only does that for the one channel that contains the information we really care about. All the other channels it gives us, which tell us about the systematic errors, we get an honest answer. It's really, really helpful. It's hard to do precision metrology without doing that. What it does mean, though, is that you have an enormous, you can be working on an experiment for many, many months and have no idea where you're going. It builds up a lot of suspense. Here is limits on the electron-electric dipole moment over many decades. You can see this is sort of the Gene Cummins. This is the Eugene Cummins era here up at Berkeley when he was adding several orders of magnitude onto accuracy. This is the beginning of the molecule era. The Imperial College people sort of pioneered a lot of atom techniques. We got into the business with a crude initial measurement. The Acme group, the Harvard-Yale group, had this measurement here. Just a couple of years after that, we had sensitivity equal to the Harvard-Yale group, and we were going to have to reveal it. The Harvard-Yale measurement was consistent with 0. We realized that we had taken a year's worth of data. We were about to unveil the data, and because the Harvard-Yale group had an answer which was consistent with 0, the stakes were very high. We would either reveal that the Harvard-Yale people had done it right, or maybe they had done it wrong, and it would have been very embarrassing for the Harvard-Yale group if they had done it wrong. So we felt very strongly that it was an important measurement. There was a very, very tense moment when we all got into the same conference room and we told the computer, stop lying to us. And it did, and we got an answer which was consistent with 0 and almost with the same error bars as the Harvard-Yale group. At that time, these two measurements were a factor of 10 larger than the earlier measurements, and they were sort of contributing to they were among the things which were contributing to the, I won't say demise of supersymmetry, but to its becoming less fashionable. The LHC wasn't seeing anything. These dipole moment measurements weren't seeing anything at the scale sort of that would have fit very naturally in the scale of supersymmetry. Doesn't mean it's wrong, just means there's just one more thing not going in this direction. Then, just a few years later, as we were working along, what did Harvard Yale do? They made a measurement which was 10 times better. Very frustrating. This is one of my favorite television shows. That's just rude that they did that. We felt that we had to catch up, and we almost have. We are within, as I say, we're probably within just a matter of a few weeks of taking the last of our data and getting a measurement which will again be at a very similar accuracy. And again, we'll find out whether Harvard and Yale's measurement, which is consistent 0, was correct or whether they made a big mistake. It's entirely possible they measured 0, which was the sum of a large electric dipole moment and a large systematic. They added up to 0. We can't rule that out, and we'll only know that after we make a measurement too, which will be about there. But it may or may not be. It may be a limit, and it may be a measurement. Oh, we are heading soon, I hope, but with a longer time scale, towards a measurement which is about another factor of 20 better. How are we going to do that? We're building a much larger experiment. For us, this is now big science. It's big science because the length of the experiment is longer than a graduate student. So you know it's big science. That 6-way cross you see there is more massive than my least massive graduate student, which is also tells you something about, like, you know, when you start having to use hoists in your experiment, that's a breakthrough of one kind or another. That long thing there, this long arm of the experiment is going to be wrapped in styrofoam and chilled to about 150 Kelvin, which will reduce the blackbody radiation and give us correspondingly much longer coherence times. And inside that long arm there, which is about a meter long in this version of the experiment, instead of having one ion trap, we will have dozens of ion traps. You can see it here. Basically, there are a series of rods running the length of the trap, and we charge them to cause a rotating electric field, which is sort of in the plane of rotation is along like one of those black lines. Each of those black disks is a separately chargeable electrode, and every 4 of those disks can create a little ion trap. So we're going to fill this up with dozens of traps, dozens of little clouds, and run them all in parallel. So a combination of longer coherence times. We get away from the space charge limit by having many little traps instead of one big trap, which ends up where the space charge becomes very inconvenient. And we should get another factor of 20 in precision. And that's coming 2 or 3 years. As I say, one measurement is coming in 2 or 3 months, and one measurement is coming 2 or 3 years. 2 or 3 years in research advisor time, which could be as many as 5 years. I don't know. The graduate students feel that I'm overly optimistic. I don't know what they're talking about. Speaking of the graduate students, oh wait, okay. Yeah, so if we were to get to this sort of, this lower improved precision, where we are heading, there's a 3rd generation of Acme experiment. Groups here at Caltech and elsewhere are trying to get this. We start to become sensitive to particles with masses, you know, in the tens of TeVs. Okay, these are distinctly model-dependent limits, so this is not a promise, but like, you know, there exist sensitivities depending on the nature of these particles as yet unseen. Yeah, so this is done by, we'll just meet them again, the graduate students. We no longer meet on Zoom, which is fun, but we still have a Zoom picture. And really, I just want to reemphasize that it's the creativity, ingenuity, and hard work of all those people that make projects like this work. And at this point, I'm going to stop and thank you for your attention.
All right, thank you very much. If you have questions and you're local, please just raise your hands. If you're remote, try to put them in the chat window or raise your hands, and I'll do my best to keep an eye on you. Yeah, up there.
I have a really basic question. I apologize. I admit that this is the first time I've ever heard of the possibility of an electron-electric dipole moment. Though I should have. If your graph goes back in measurements to 1965, that's a hole in my education. If you measure one, is that evidence that it's a composite particle?
That's a good question, and it's a little bit of a definition thing. The way I would think about it is that the electron is at its heart a point particle, but that as you get closer and closer to the point of that point, there are very large electric fields, and it polarizes the vacuum around it. And when I say vacuum, I don't just mean the vacuum, the electromagnetic vacuum, but the vacuum associated with many other particles. And so there would exist, or there does exist around the electron, we'll call the bare electron, a sort of snowball of transiently existing other particles, and some of those particles are basically where the electric dipole moment lives. So that snowball is definitely a composite particle, but that applies to everything, and certainly anything with a charge. What you're hearing is an atomic physicist, basically, I work with lasers and oscilloscopes and stuff like that. My education in real particle physics is scandalously low. So you're getting more or less the Scientific American answer to that, and not what a serious high-energy particle physicist would tell you. And for that, I apologize. But I'm standing here, so I have to do the best I can.
Would you mind letting me into the room? I got kicked out.
Yeah, fine.
Kicking myself out. No.
Can I admit all? I'm admitting
Admit all, yeah.
Okay, I don't know who I'm admitting, but you should be back in. Are you there?
Thinking about it.
Joining.
In the meantime, any other local questions? Yes.
So you mentioned earlier that you don't really have to worry about magnetic fields, but there was a slide that you briefly glossed over that kind of implied that that might not be the case. When do you have to worry about magnetic fields?
Starting just about now, as it turns out. In this, I told you about this generation experiment, which we anticipated in about a month. That experiment would have been easier had we had new metal shielding around our experiment. And it's a source of some mortification to me, because I hate new metal shielding, and it was something I was always very, very proud about. I would go around saying like, we don't even have new metal shielding. That's how intelligently designed our experiment is. But in fact, we had to go to some hassle. And for a new generation, which will be a factor of 20 higher, yeah, it's going to have to be shielded. So to first order, and even beyond that, magnetic fields cancel out. But magnetic field gradients do not cancel out. And even uniform magnetic fields, in the presence of certain electric field imperfections, you can get cross terms that end up sort of giving you the effect of the magnetic fields counting again. So yeah.
So it's still like mostly DC or like DC gradients. It's not like you're sensitive to like magnetic fields that are oscillating quickly. You have like, you know, still like
the thing is inside a big steel box.
Yeah. Okay.
So there's no, which is not, it's not as good as being in a copper box, and certainly not as good as being in a superconducting lead box. But at 300, the relevant frequencies are hundreds of kilohertz. So there's not a lot of magnetic field noise up there getting through the metal.
We have a remote question. David Hitlin, I think you're unmuted. You can just go ahead and ask. Oh, so,
I might have had my sound down.
oh, just give us one moment and we'll...
Hang on a second. I actually don't know how to do this.
Okay, hold on. I think I can...
It's for some reason not... maybe I have to click.
How about now, David Hitlin, ask your question and I think we'll be able to hear you. I can hear you.
So the question is, to what level of precision do you have to ensure that the fins are in fact radial?
I think what I...
If they were canted, then you're up to generate a frequency displacement where you put the ion.
Yeah, so... Oh. Did you turn that off? How about now? Good. Question is, how precisely radial, those fins are sort of coming out radially, how precise does that have to be? And the answer is, it has to be pretty good. we can see a lot of the imperfections in these auxiliary measurements we make. And the nature of the experiment, the fact that we simultaneously are doing spectroscopy on the molecule aligned one way and the molecule aligned the other way, the location of the ions is basically driven by the monopole moment of the ions, which is just -1. The gradients in electric fields dotted into the molecular dipole moment is not enough to move the ions around very much. So we get a lot of natural cancellation from some of those effects. I showed you some data that shows you what happens if, in that particular case, what happens if the fins are not long enough, and you get fringing fields coming in from the edges of the fins. So it matters some. One of the big problems we have is that as we cause the electric field to rotate under larger and larger fields, there's an effect known as the ponderomotive energy, which is basically like a well, it's a ponderomotive energy. I don't know exactly how else to describe it, which basically looks like a repulsive energy for the ions, a potential energy, and if there's a gradient in that, it can actually cause the ions to fly out of the track. So that's one of the more stringent things, which is most stringently driving the precision design and construction of the fins. Yeah.
Echo? You mentioned the multi-cell, multiple tracks.
Yes.
And you also mentioned in your present track, you sometimes run it one way and sometimes run it the other way.
Yeah.
Did you consider, or can you do, in your multi-trap, some of them going one way and some of them going the other way as a way of canceling some systematics?
No, we can't, just because the traps are close enough together that they would sort of sense the rotating field from the adjacent ones. What we can do is do it for a little while one way and then do it for the other way. We are looking into the possibility of having the direction of the magnetic field oscillate from one. So basically, it's sort of like a sort of like a rotating, sort of oscillating quadrupole gradient. And then that could. What we actually do, I didn't emphasize this, is the ions start on one side, and it's kind of like a bucket brigade. We make the ions, we prepare them, we load them into this little conveyor belt, and they go along evolving in a quantum mechanical way, and they come out to the far side and they're probed. So at any given time, we have atoms which are 1/4 of their way, 1/4 second into a Ramsey fringe, 5 seconds into a Ramsey fringe, 15 seconds into a Ramsey fringe, and out. And it would actually be super useful from a noise point of view if as the electric static fields that move the ions along move along, there was a similar conveyor belt that was sort of moving magnetic fields along, alternating their directions. It would give us some nice cancellations. It would involve having a lot of time-varying magnetic fields inside our cold world, inside our cold world, and their corresponding eddy currents and heating. So we are thinking about it. Yeah.
There is some CP violation in the standard model.
Yes.
Were you able to see it in your experiments?
So the question is, there is some there is some CP violation in the standard model, and the answer is no. It is another 8 orders of magnitude smaller. So I would like to pitch this to you as a good thing. What it means is that when we see CP violation, we don't have to subtract out the standard model background. Oftentimes in precision metrology, you make a very precise measurement and you have to subtract a large number which you've calculated. And you wonder, like, is my error in my calculation or in my measurement? Here, the calculation should be 8 orders of magnitude less than our precision sensitivity. I say that to put a brave face on it. It would be very nice to see a CP violation which was predicted by the standard model, because then you could say, yes, there's a sanity check we're seeing, but we'll never get there. 8 orders of magnitude is just a long ways. Yeah.
This bucket type experiment you described, is that like a continually running operation, or is it
Yes.
done in sort of pulses?
Well, it's in the sense that the buckets are discrete. So about 3 times a second, we load a bucket, and there's about 25 buckets, give or take, or you work it out. They'll be sort of cruising down there. When we have the buckets all full, it may slow down to about every half second or so. So our lasers, as it turns out, pulse 10 times a second. So we have sort of a discreteness in when we can readily bake them, and also when we can readily probe them. But there's sort of a wide range of how fast the bucket brigade can travel. We can sort of gradually slow it down and probe longer and longer coherence times and sharper resonance lines.
But so up to that, you can sort of run it for weeks or months, just sort of continually.
Yes. Yeah. We would have to change the direction of rotation. You'd have to stop making the ions, let the last of the ions come all the way out and fall out. If you tried to change the direction of rotation in the middle, bad things would happen. You'd have to fall out, start loading them. So you would have, or if you change the direction of the magnetic field, there's various things that you'd have to sort of stop to do. So you would probably let the thing run for 5 or 10 minutes with one configuration, change the configuration, let it run for 5 or 10 minutes, like that. Yeah.
So you mentioned at the beginning that one way to keep like these ions trapped was to like use a particle accelerator like in a loop.
Yes.
And you ended up like doing something very small. But like what about like using a real ring like in particle physics? Like as I guess that hasn't been done, but like would like the sensitivity be like around the same or is it like not really known?
It's funny you mention that because right when I was in 2003, when I was thinking about this experiment, I conceived it as a storage ring. And then I found that the parameters I wanted to go to were slower and slower and smaller until it became a millimeter. And then I thought, why have a ring at all? Why not just have a rotating electric field in a much bigger? But the original version of this bucket brigade was in fact a storage ring with bunchers. And so instead of being a bucket brigade, it would be packets in bunches. And they'd get loaded in and they'd get kicked out. And then I started working on that. And it turns out that there's this whole enormous literature of people who do accelerator physics. And it's really hard. And if the bunches talk to each other a little bit, there's all these instabilities. And I realized that I would need to be not one person. Basically, I would have to sort of reinvent all of sort of storage beam physics. And I wasn't ready to do that. That could be a future generation, but I thought I needed either to like basically collaborate with some people who do all that, which I could see doing in the future, or I needed something much simpler, which in this case was just kind of plodding along. Yeah.
But do you think it can still be competitive with current measurements?
Sorry?
Do you think it can still be competitive with current measurements?
Which one?
Like if we use like a storage ring?
I think it could be, in principle, it could be very, very good. Like at least in terms of its statistical precision, it could be awesome. I had spent 15 years thinking about systematic errors and traps. And it's not a very big jump to go from a trap to a trap which is moving along at a speed of about 5 centimeters per second. It's a really big jump to go from that to something which is going around in a circle which is several meters in diameter, thousands of times per second. That's a really big jump, farther than I thought like everything we'd have to start fresh from understanding whether the final measurement was accurate or not. And I thought it's too big a jump for us. Yeah.
What are the prospects of using other features of quantum mechanics to enhance the sensitivity? So instead of measuring one condition and then the other, prepare some superposition or entangle the ions to enhance the sensitivity?
Yeah, these days using quantum enhanced readout for trapped molecules is very, very trendy. And then, entangling them to get higher precision also. Typically that sort of thing is done on numbers of, 4, 5, 10 ions or something like that. And it's usually done in a place where you can laser cool the ions to sort of millikelvin ground state kind of temperatures. Here, because we have to have the rotating bias field, in the lab frame, the natural velocity of these ions is many hundreds of meters per second. And yes, in principle, you can be traveling many hundred meters per second, and in that frame have temperatures of a millikelvin. But it ain't easy. If you're driving around a racetrack at hundreds of miles per hour, if your racetrack is even a little bit bumpy, you're not going to have a smooth ride. So we if we were willing to do it with a small number of ions, like just 5 or 10 ions, and think of a way of getting around this problem of the rotating bias field, maybe. We are operating with 500 ions, so you have to do a lot of squeezing to do better than the square root of 500. That's already pretty good. The quantum projection limit is not too bad on the bunch, so you have to actually be squeezing pretty hard to take advantage of that. People have done it, but it's on top of everything else. We already have a lot of constraints. I put it that way. There was a question over, yeah.
Yeah, maybe you mentioned in the introduction, but what new physics, or what physics can be ruled out after additional factor of 20 limit on the
Yeah,
electron?
so at this point, I would say that sort of high energy physics phenomenologists, theorists are very, very creative. And so it's almost the other way around. Like if we were to see a measurement, they can construct a universe around it, or many universes around it. What you'd really like would be non-zero values of the electron-electric dipole moment, non-zero values of the neutron-electric dipole moment, maybe of the mercury nucleus, which has got a little bit, has additional structure to it. Maybe the muon. There'd be a lot of, what you'd really like to do is have many things coming in from different directions in order to, in an experiment like this, you're never going to get the kind of visual result you got from the early days of scattering experiments, where you actually had like tracks of new particles. I think those days are gone. They're probably gone too, even in particle physics. It's a much more inferential sort of thing than it was back when. It's like, look, there's a muon. Look at the radius of the circles. It spins out. That's how massive it is. I don't think that happens anymore. It's more like I see an enhancement in a production of muons, and that tells us about something else. But even these accelerator experiment could give you a lot of really rich information. We're going to give you a number. So, but what we might be able to do is, right now, if you wanted to build a new accelerator, do you build it 5 times more energetic, 20 times more energetic, or 10,000 times more energetic? I don't think there's a really good story for any of those numbers right now. If you had some of these other measurements, you could do a sort of more targeted version of high energy physics, which right now is, my impression is challenged for that reason.
Well, let's thank our speaker again.